Most agent architectures are built by duct taping disparate pieces together, system prompts in one file, JSON schemas in another, and workflows holding them together. As engineers add capabilities, they add tools. Each new tool requires a detailed JSON schema, bloating the context window before the model even generates its first token. To execute those tools, the framework relies on brittle XML or regex parsing to extract arguments from the model's text, a process prone to syntax errors and hallucinated parameters. Scaling this design means writing and maintaining exponentially more schema configuration. The architecture buckles under its own weight. Modern agent harnesses have become deeply fragmented. Building AI systems has turned into an exercise in JSON schema management, rather than true system design. NVIDIA-labs object-oriented agents, NOAA, rejects this fragmentation. Instead of configuring an agent through scattered files, you author it as a single native Python object. The agent is the class. This design drastically restricts the interface, collapsing the entire tool registry down to exactly 2 tools. Every capability, every piece of logic, and every step of planning is forced through stateful Python code execution. This shifts the primary engineering challenge. Instead of wrestling with context prompting and schema alignment, developers must focus on securing the execution environment. NOAA trades schema complexity for runtime execution authority, providing the foundation for a highly constrained code-driven LLM loop. NOAA repurposes standard object-oriented primitives to route the LLM. The class docstring literally serves as the model's system prompt. Edits here change behavior directly. The type-hinted method signatures act as strict tool contracts. The structural trigger is the Python ellipsis, used as a bare method body. At class creation time, a metaclass called agent meta intercepts any method body ending in that bare ellipsis. Agent meta silently rewrites it into an LLM generation method, injecting the AI's output into the code path. Because this happens during class creation, entering the autonomous loop requires no special framework initialization. You simply call await agent.solve. The developer experience remains pure Python object-oriented programming. The underlying LLM API integration is completely abstracted away. This diagram shows the React loop that powers NOAA's runtime, operating on a simple while-not-exhausted cycle. Each turn, the LLM is offered exactly 2 tools. The first is execute Python, the sole action surface. The second is return result, the sole termination surface. To stop iterating, the model must explicitly call return result. NOAA strictly validates the model's provided value against the method's pydantic return type annotation before accepting it. If it fails, the error feeds back for a retry. The standard industry practice feeds the LLM dozens of distinct endpoint tools, each eating into the token budget. NOAA limits it to 2. Restricting the interface eliminates schema bloat entirely. The burden of success falls directly on the model's ability to autonomously write valid Python. When the LLM calls execute Python, its code runs in a Jupyter-style REPL environment, where cell outputs persist across turns. The LLM is automatically bound to self, allowing it to access its own methods and attributes natively. External capabilities like model context protocol servers are compiled into dynamic Python classes.
The model interacts with them via code execution, rather than direct LLM tool calls. Because the model writes code iteratively, NOAA rejects the standard append-only chat transcript for context management. This visual maps how the context window is reconstructed dynamically from the event log every single turn. To keep this bounded, a token budget summarizer monitors the context limit and automatically compacts older events to save space. If an API provider hard rejects an overlong prompt, an archive on error fallback aggressively drops older logs to recover. Rebuilding context dynamically ensures the LLM's view stays strictly consistent with the current REPL state, maintaining accuracy for complex multi-step operations. Letting an LLM write and execute arbitrary Python directly on a host machine exposes systems to severe risk. NOAA responds with layered permissions. The first defense is a set of static AST validators that scan generated code to block exec, eval, and dunder introspection. The second layer strips dangerous capabilities from the execution namespace, outright blocking modules like subprocess and socket. NOAA acknowledges an architectural reality.
These static checks are defense-in-depth guardrails. They are not a true containment boundary. True containment requires an OS-level sandbox utilizing landlock and setcomp to physically restrict the process from the host file system and network. Crucially, this sandbox is strictly opt-in. NOAA's default configuration runs an in-process backend, granting the LLM the host's full operating authority. The framework is entirely transparent about this vulnerability. It forces systems architects to explicitly engineer OS-level isolation, rather than relying on false security from the framework itself. For long-running tasks, NOAA offers an optional memory subsystem backed by a dual SQLite and vector database architecture. Standard agents suffer from zombie memory. When live state data is copied as strings, it rots, becoming stale and disconnected from the environment. NOAA solves this with a strict pass-by reference rule. Instead of storing raw values that decay, the system stores a reference pointer, like a file path. At recall time, these references force the system to read the live state immediately before generating the next prompt. This mechanism pairs with dedicated reflection and forgetting engines that consolidate insights and evict outdated logs. By rereading live state on demand, the architecture eliminates hallucinations caused by outdated context. The memory remains factually accurate over extended sessions. NOAA discards the configuration file. The harness is authored directly as a Python object, utilizing a metaclass to silently inject the LLM into the execution path. Massive tool registries are abandoned. The model navigates its environment through a single CodeAct REPL, utilizing exactly 2 tools. And containment is explicitly environmental, demanding engineers actively implement OS sandboxing to secure the permissive default state. This framework is built for engineering teams who want to leverage native object-oriented programming rather than managing proprietary JSON orchestration protocols. Replacing schema complexity with pure execution power requires rigorous environment design. But for those who master it, NOAA provides a powerful blueprint for the next generation of native AI agents.